Hello everyone. We'll be just starting in a couple of more minutes. We'll be just waiting if some more people would join or not. Thank you. Okay. Very good afternoon to everyone present here. My name is Saurabh. I'm from Stereo Universe. So today is the final talk in the exposure series in astrophysics and cosmology. So today's talk will be given by Rishabh Jain. He's on the topic adaptive optics, the art of shaping light. He is currently a bachelor student in Kirorimal College, University of Delhi. So we can start. Over to you, Rishabh. Now.
Yeah, so hello everyone. Thanks a lot, Saurabh, for giving me this opportunity to present a talk on adaptive optics. So recently there have been these talks on various interesting topics. Though this topic is not much theoretical, but it is a technical aspect of astronomy, that how we can produce high quality images by sitting here on the earth, ground based telescope photography. So I would like to start it. Saurabh, is my screen visible?
Yeah, it's visible.
No, slides are visible.
Yes, yes, it's visible.
Now, yeah, it's okay now. Yeah, so here's the first diagram I want to show. This diagram shows the variation of atmospheric opacity with the wavelength. So we can see that there's a lot of atmospheric turbulence in case of lower wavelengths, but there's a small window here in the optical wavelength, and it's clean here in the radio waves, as radio waves can penetrate out through the atmosphere and can give results to high quality images, as we saw in the case of black hole, the event horizon telescope that gave us the first image of black hole. But there's a small gap in this optical band also, but there is a small turbulence also. So what happens is, when the light waves comes from a distant object, they enter Earth's atmosphere, they get distorted, and this distortion may lead to low quality of images. Let's see how. Let us look at what limitations are imposed by the Earth's atmosphere. Number one is opacity. Since the radiation or the light at certain wavelengths are absorbed, they produce local thermal radiation, which causes loss in the opacity. Another thing that is lost is the luminosity due to scattering of sunlight, broadband radiation, air glow emission, and all these things. And of course, the turbulence by the movement of solar winds and all these things. So, these things can create a lot of turbulence or the distortion, we can say, to the light wave, to the wavefront of the light waves coming from a distant source, right? What an how an astronomical object looks like is generally a point source, infinitely small source of light, and energy propagates in the form of spherical rays in the space. We have studied this in the in classes of 11th, 12th, and all you know these things. So a wavefront is an abstract representation of the phase of a propagating wave, like how the light is traveling in the space. So we can see that suppose there is a small point source, spherical wavefronts are emitting out of it. Point source and spherical wavefront is emitting out of it. And these are plane waves. Okay. So now I want to talk about how an image is formed in a telescope when there is no turbulence. So this is a diagram of Ritchie telescope. The difference is just that here we use hyperbolic mirrors instead of parabolic mirrors as used in Cassegrain 1. So the light comes from the infinite source, and an image is formed at the telescope. The purpose of a telescope is to collect light from the astronomical objects and focus it on the detector. The detector can be any CCD, or we can see it directly through the eyepiece or whatever we want. So the telescope collects the part of the wavefront, the area defined by the diameter of the telescope. So what happens is that how much light the telescope will collect is determined by the aperture. The aperture or the diameter of the primary mirror is of the telescope. The larger is the aperture of telescope, the more light it will gather. So we prefer the telescopes of larger aperture to gather more light. And the magnification of a simple telescope is generally the given by the ratio of aperture and aperture of the telescope and the eyepiece length and the aperture of eyepiece. So suppose I have a telescope of 650 millimeter focal length and I am using 10 millimeter eyepiece to view any object like moon or anything, Saturn, Jupiter, whatever. So the magnification will be of 65 times, like 650 divided by 10. So 65 times will be magnified image. And the angular diameter of the image that is formed inside the telescope, that is determined by the diffraction of light, and it is given by theta is equals to lambda by d, where lambda is the mean wavelength of observation. So generally if we observe in the optical wavelength, so lambda is like 500 to 700 nanometer, and d is the diameter of telescope, the aperture that I'm talking about. So these are the diffraction pattern known as Aries rings or Aries disk pattern. The core is the PSF. PSF is the point spread function. That is the most bright, most intense. It contains the most of the intensity in the center, and it gets faded as we go far from the center. You can see in this representation that there is a peak intensity at the center, and then it gets decreasing constantly. So what's a PSF? Point spread function is the irradiance profile in the image of a point source. It is the response of system to the incident plane wavefront. What it means is that to tell how much angular resolution a telescope that we are using can provide us. So this is the most important thing when we are imaging through a telescope, especially while sitting on the Earth. Now, how an image is formed in a telescope when there is no turbulence we are talking about. So we must have heard of this full width at half maximum, which is the measure of width of an object when the object does not have sharp edges. We consider theoretically we consider the case that there is a no turbulence and image of a star has a profile closer to a Gaussian distribution as I've shown in this figure. So the best possible angular resolution that can be achieved by an optical telescope is given by theta is equals to lambda by d, as I told earlier. So let us take an example that I have a 10-meter aperture telescope. Now let's talk about the larger telescopes with the large diameters like 10 meter, 30 meter or so. So in the case of a 10-meter telescope at lambda is equals to 1 micrometer, you can get an angular resolution of 0.02 arc seconds in case of no turbulence. So which is pretty good. Like I think it's pretty good. We can get a good, highly resolved image of some distant objects. But what happens in the case of turbulence? The same image size is typically 0.5 to 2 arc seconds. The angular resolution is increased. So the lower is the angular resolution, the more clear image we get. But what turbulence causes, it increases the angular resolution so that we can't get much clearer image. The larger the diameter of the telescope, the smaller details can be seen on the object that is being observed. Hence, better is the resolution. If and some of you have used the telescope, you must have seen these spider arms. These are known as spider arms, where the secondary mirror is attached. So here you can see that this is a telescope, basically a reflector one, and behind behind that there is this primary mirror, and the spider arms, mm, and through the spider arms, the secondary mirror is attached. What happens is that these spider causes the diffraction of light, and the diffraction limit is the theoretical limit of how smaller details we can get through through the telescope we are using it. So that is a simple phenomena that since the light is being coming, and it will strike the spider arms for sure, and because of which diffraction will take place. And one more thing, this is known as the diffraction limited image. Theoretically, we call it a diffraction limited image. So what happens when plane waves meet the Earth's atmosphere? Since atmosphere is constantly moving, temperature fluctuations in small patches of air cause change in index of refraction. So what happens is that the plane waves that are coming, the straight ones, when they strike the atmosphere or they come in the contact with the atmosphere, they get distorted. Instead of getting these plane wavefronts, these straight ones, we get some curvy or distorted wavefronts. We call distorted wavefronts. Okay, so plane waves are distorted when they reach telescopes. They are no longer parallel. So, and we know a basic concept of optics that when on the parallel beams of parallel rays are parallel rays hit their lens, they are focused on the focus point in the focal plane. But since they are no longer parallel, the image is blurred. You can see that these parallel lines, they converge at a single point and we get a sharp image. But since these rays are not parallel, we don't get a sharp image and the image is blurred. They cannot be focused at a single point. We get blurry image. This diagram can make it much more clear. Like this is a star we are observing, a source, and it is emitting the spherical wavefronts, and this is what we receive, the plane wavefronts we receive in case of no turbulence, and we get a focused image. And here we can see peak, peak intensity. And in case of turbulence, these wavefronts are distorted and they are no longer focused, and we see that the mm, peak that we were expecting, that full width at half maximum lambda by d, is now spreaded. It is now spreaded across all over here. This is the diffraction limited, the theoretical image that we were expecting, and this is the seeing limited image that we are getting. The function is spreaded across there. Now we are getting the highest resolution that we can get is lambda by r naught. R naught is known as the Fried's parameter, which is the coherence length of the place where we are taking the observations. All right. So instead of diffraction limited, we are now getting seeing limited images. So you can see in this image, we were expecting this image is this image is of binary stars, pair of binary star systems, and we were expecting these images like theoretical limit known as diffraction limited image. But what we get is this blurry thing, and we cannot resolve out of it that there is a binary pair of stars. So earlier there was a peak, but now the function is spreaded all over it. And at the best atmospheric conditions, they're at the disk diameter of 0.4 arc second at high altitude such as Mauna Kea Observatory. So these images were taken at this blurry image was taken at Mauna Kea Observatory in Hawaii. It is the most famous place, and there are many large ground-based optical telescopes like Keck Observatory, Subaru Observatory, and the upcoming 30-meter telescope will be placed at Hawaii itself. So, okay, correct. And the turbulence strength is characterized by quantity R naught that I told is the Fried's parameter. This is not French parameter. This is Fried's parameter. I just made a mistake. So R naught is the turbulent scale size within which the air is uniform and there are no phase distortions. like the limit with which there are no phase distortions. So that's why we refer it as the coherence length, and it is generally 50 to 30 centimeters at the good observing sites, like is around 20 for the Mauna Kea at Hawaii. So let us say if R naught is 10 centimeter, the full width at half maxima will be around 1 arc second at 0.5 micrometer. So earlier what we were expecting was to be 0.02 arc second. Now we are getting 10 arc second. So you can see that the theta is increased, and the angular resolution is and thus the angular resolution is increased, and we cannot resolve between the two objects. Yeah, so that's what I was saying. Like, suppose we have two telescopes, D1 and D2, and D1 is 10 meter and D2 is 4 meter. So full width at half maxima is lambda by d. We are observing at optical band. Lambda is equals to 0.5 micrometer. So the angular resolution what we get from the respective telescopes are 0.01 arc second and 0.03 arc second. But if R naught is given by 20 centimeter, and these calculations are without the turbulence factor, and R naught adds up the turbulence factor. So if the R naught is 20 centimeter, then full width at half maximum will be lambda by R naught, that is 0.5 arc seconds, which is at Mauna Kea, instead of lambda by d. So it doesn't matter if we have the telescope of 4 meter, 10 meter, or maybe much larger, 20 meter or 30 meter. We cannot get much more better resolution than 0.5 arc seconds. So any telescope with diameter d greater than R naught has no better resolution than a telescope for which d is equals to R naught. This becomes useless to make the aperture of telescopes more larger to get better resolution. But still, we have one solution for it. Let's see. So in short, the turbulence distorts the wavefronts, spreads the energy received into a diffuse disk, reduce the peak intensity, and it produces the seeing limited images. Now, what's the solution? And the solution to this is the adaptive optics. Adaptive optics, it can undo all these object effects, and we can get back the diffraction limited image. Now let's see how. Adaptive optics is is a modern technique. How it works is we have a telescope. There's a deformable mirror in the telescope, and the wavefronts come through beam splitter, which one part is sent to imaging camera and one part is sent to wavefront sensor and the control algorithm. These deformable mirrors are so fast that they can move at 100 to 1000 movements in 1 second, according to how much distortion it is taking place by the atmosphere. And this is the feedback loop. So suppose these are the light from the telescope. This deformable mirror changes its shapes in the direction opposite to the distortion, and then we get the proper image. It will be more clear by this animation video. Let me play it. Yeah, so a sodium laser is fired from the telescope, and it is thrown up into the air at high altitudes like 50s, 90 kilometer above the ground, and it contains a sodium layer which ionizes the sodium ions up there, and we create some artificial stars out there. And then light from these artificial stars, yeah, like we can see here this laser guided star. This artificial star is known as laser guided star, and we now we measure that how much distortion is caused by atmosphere on this laser guided star. Now the light from this laser guided star falls on the telescope. This animation is of GEMINI Telescope at Mauna Kea, and this is the adaptive optics technique. from inside the inside view of adaptive optic system. So these wavefronts are coming from that laser guide star, which which will be distorted. This is the imaging system. Yeah. So this is a beam splitter. So we can see that there is these distorted wavefronts coming out of that laser guided star, and we are seeing a turbulent image. Yeah. So this image is the turbulent one. That's too much blurry, too much shaky. Yeah. So these are these distorted wavefronts coming out of that laser guided star, and through this feedback system, the data is sent to that deformable mirror, and it changes its shape in the direction opposite to distorted wavefront very quickly. And these wavefronts are now corrected. So you can see what in the output what we get is the corrected wavefronts, and now the image, we get a proper image with a proper peak. All right. So these were the distorted wavefronts that were coming onto the deformable mirror. The deformable mirror changes its shape according to these distortions, and then we get the outgoing corrected wavefronts. That was the video that was playing in that image making device. So let me play it. Yeah. So earlier it was that blurry, and after the adaptive optic system was turned on, we can get a proper image. You can see, right? Okay. So turbulence is distorting the wavefront as we discussed earlier. It spreads the point source into a diffuse disk, and it reduces the peak intensity, and it produces the seeing limited image. Uh, and when the AO is not applied, we can see a flat peak. Not it's not good to say peak. We get a diffused disk. But when the AO is turned on again, we can get back a peak as we expected earlier. So in this image, you can see that this is blurry image, and when we turn on AO, can get a focused image. Okay, so how adaptive optic system looks like? So this is a model of Subaru telescope, 8-meter telescope at Mauna Kea, Hawaii. So this is how an AO system looks like. This is the laser room through which laser is fired up, and here's the primary mirror, secondary mirror, and the data is sent to this AO system. And how big it is? It is as much as big as a man. These are some original images from the Subaru telescope adaptive optic system. Yeah. So adaptive optic system lives here. This is from Keck telescope. Keck is a 10-meter telescope consisting of segmented mirrors. Here's the primary mirror, primary 10-meter segmented mirror, and light coming from the distance source, and secondary mirror, and the light is then focused onto tertiary mirror, which turns it towards that adaptive optic system. And from here we have this deformable mirrors to correct them. It's, yeah, so this is a person. So you can see how large is the aperture of this Keck telescope is. Keck is 10-meter telescope. It contains 36 hexagonal segments. So it is very large. So one segment is about 1.4 to 1.5 meters. So it's very large as compared to normal human being. Yeah, so here are some results of adaptive optics. Like This is Neptune in the infrared, captured by captured at the Keck Observatory. So without adaptive optics, it's look just like it looks too blurry. But when adaptive optics is applied to it, we can get a much more resolved image of Neptune. And this is the image of Keck observatories at Mauna Kea. These laser beams are sodium lasers are being fired out, and you can see another images of the Saturn. This is of Uranus, and without adaptive optics and with adaptive optics, you can see that you can get much more clearer images with the adaptive optic system. And another example, this is the galactic center, the center of the galaxy. So without adaptive optics, we can't see much of the details. That is not a resolved image, that's a blurry image. But with adaptive optics, we can see this clear image, a pretty much clear image as compared to that which was without adaptive optics. And this is image of Gemini telescope. And again, the sodium laser is being fired out. Gemini is also at the Mauna Kea. Yeah. So this one is through Subaru telescope. This is Subaru telescope, and you can again see this sodium laser that is, which creates laser guide star. And without adaptive optics, we can't resolve anything. But with adaptive optics, we can resolve a lot of things as shown here. Yeah, this is Shane. Shane is another telescope, and you can see that some more results of adaptive optics. Like it was blurred earlier, but then it was much more reserved. Yeah, so from Lick Observatory, Lick is 1 meter telescope at University of California. That's a long exposure image, and that's a short exposure image. So long exposure spreads the wave function, as we saw earlier, into a diffuse disk. Short exposure image doesn't gives a lot of details. And when we apply adaptive optics to the imaging, we get a peak again. That was we were expecting, that diffraction limited image we get back. Yeah, so these are some current and future ground-based telescopes. Mm, Yeah, so this is very large telescope, 8.4 meter telescope at Europe, made by ESO. So yeah, and this is Keck, 11 meter telescope. Yeah, I missed that earlier. Keck was 11 meter. Keck is the 11 meter telescope. It's currently in the operation, and it contains segmented mirror. Keck was the first to get segmented mirror technology. These hexagonal mirrors, these are segmented mirrors. And some of knowns are Hubble Space Telescope, that is about 2.5 to 2.6 meter in the diameter, and Herschel telescope is 3.5 meter, and James Webb telescope that we were expecting earlier to get in 2020 or 2021 is still postponed to launch further for 5 to 10 years due to this pandemic condition. And this is TMD, 30 meter telescope. This is being built at Hawaii. It was also we were expecting it to be launched till 2025 or so, but again we didn't get it. We didn't get the chance to get it. Yeah, and this is EELT, extremely large European space telescope, European extremely large telescope. Sorry, and this will be of 39 meters. You can see the evolution. Earlier we were having 8.4 meter, then 11 meter, then 30 meter, and now 39 meter telescope. It will also contain segmented mirrors. Segmented mirrors are used because we cannot take a complete whole 30 to 40 meter large primary mirror at a place up on the mountains directly. So we use that, yeah, so we use this segmented mirror technology to make the primary mirror of the telescope. Yeah, so this is the image of European extremely large telescope. telescope. So how it will look like, some you can see the size comparison here, how tall it will be some 100 meters tall itself. The observatory will be some 100 meters tall itself, and yeah. So, and this will be TMT, 30-meter telescope. 30-meter telescope, as I told, it is being built at Mauna Kea, and the partner countries are USA, Canada, Japan, India. India is contributing a lot to it. India is producing about 1,500 actuators and support assembly segments for TMT, 30-meter telescope, and the software to control the telescope is being supplied by India, and all there will be 492 mirror segments. These mirrors will be placed on mirror segments, and all the 492 mirror segments are being made in India. And also these to move them, to move these deformable mirrors, there are actuators and SSGs. So all these 1,500 to 3,000 actuators and 3,000 SSGs, they are being made in India, and three organizations, IUCA, IAA, and ARIES, are collaborating for the construction of these parts in India. And these are some references. So you can, if you want to study adaptive optics in much detail, I would prefer this book, Adaptive Optics by Hardy. That's a very good book. That they start from the scratch. From the beginning, you can get from the basics, and this is a good book to refer. So thank you. I would like to end my talk here. Over to you, Saurabh.
Thank you, Rishabh, for such an enlightening and such a wonderful talk. Let's have questions now. If there are any more questions, they can just put it in the comment box.
Yeah, Saurabh, I can see a doubt. Does hyperbolic mirror refer to the shape of the mirror? Yeah, so hyperbolic mirror is not actually the shape of mirror. What happens is that parabolic mirrors are the parts of bigger spherical surface. Like, yeah, yeah, the parabolic mirrors, like we have seen, they are a part of bigger spherical surface. They are curved from the back, like the convex mirror and the concave mirror. So these we call as the parabolic mirrors. And the hyperbolic mirrors are the ones which are
Hello, Rishabh. Your audio is gone. Hello, Rishabh. Can you hear me? It seems that Rishabh might have some connection issues right now. I'll just wait for a couple of more minutes if he's going to join us again and answer the questions that are left. Hello, Rishabh.
yeah, yeah.
Yeah, yeah. Now you're back. Okay, so you can answer the question now.
Yeah. Can you repeat the question, please?
Answering one question, right? You are answering the question. This hyperbolic mirror if it is the shape of the mirror. We're going to take next question. We have by Namit Mishra is asking how feedback system works.
Yeah, okay. So how feedback system works? Just a minute. I am presenting my screen once again. So how feedback system works is okay. Let me try to explain by the words. If you have seen the video properly, the sodium ion laser is being fired out on and fired out in the atmosphere at much higher heights, like about 90 kilometers, and there is a sodium layer which get ionized, and we create some artificial stars over there, and then we get the light from that artificial stars, and we study that how much distortion is being caused by that artificial star, and then the feedback is being sent to the deformable mirror, and then the wavefronts are thus corrected.
Okay. So the next question is mm, how by Anup Karekar he is asking how are the X-ray telescopes manufactured and the sensors used in it.
Yeah, X-ray telescope. So frankly speaking, I don't have much idea about the X-ray telescopes, but like Chandra X-ray Observatory, I have studied about it. It is being sent to the space. We can't have the X-ray telescope on the ground, so ground-based X-ray telescopes are not possible to be manufactured. So we send them to the space.
Okay. So next question is can you contrast with active optics? Hello, Rishabh. Hello, Rishabh. Am I audible to you? Okay. He seems that the connection is still lost. He'll be joining in again. Hello, Rishabh. Am I audible?
Yeah, you are audible. Am I audible to you?
Yes, we can hear you. So, you're
Yeah,
answering
yeah.
the
So
question.
sorry for the inconvenience. Yeah, but you can carry forward the questions. Yeah.
Yeah. So the question was, can you contrast with active optics?
Yeah, so in contrast to active optics basically is that we are directly taking the observations through from the atmosphere to a from a distance source. So and that we do not apply any type of corrections and all to that to the wavefronts coming from it. Active optics we prefer for the smaller aperture telescopes. Like in India, we have 3.5-meter telescope at Aries. So there we prefer active optic system because at such small diameter and the that the turbulence may cause turbulence. Yes, the turbulence will cause the effect, but still we can counter that by some sort of technique. So in India, we are using active optic system, but in when the aperture gets much more large to the 10 and 30-meter telescopes, we prefer adaptive optics to it.
Okay. The next question is by Megha. She's asking, how do the deformable mirrors change shape? Hello, Rishabh. Hello, Rishabh. Can you hear me? Yeah. The next question is, how do deformable mirrors change shape? Hello, Rishabh. Can you hear me? Can you hear me now?
Yeah, so we have got another question that how deformable mirrors change shape. Yeah, so these deformable mirrors are placed on the mirror segment, as I showed in the picture. These mirrors are placed on the mirror support segments, mirror assembly segments, and below the mirror support segment, there are actuators and sensors, segment support sensors. So these sensors and actuators get data from the feedback system, and they can move very fast and turn the shape of mirror in any direction very quickly, and through that they change their shape.
Okay. So the next question, and I guess it's the final one. Does the corrections of distortion use something similar to a PID controller algorithm? If there's something else, can you tell it?
Yeah. So yeah, exactly. That is in the simple words, you can call it a PID controller system, PID controller algorithm itself. Yeah, that's true. There's the algorithm is not much different. There's yes, we use this PID controller algorithm.
in the case of feedback loop. Yeah.
Okay, so I see no further questions now. Uh, are there any further questions? Okay, we got one more. Manavneet is saying that why long range radio waves are blocked by atmosphere.
While long range radio waves are blocked by atmosphere. Yeah, so we have seen in that the initial slides that there's not much turbulence in the case of radio waves. They can penetrate through the atmosphere, and we have even received the radio waves from the early universe that we call that cosmic microwave background radiation. So I'm not sure about and that absorption of radio waves through atmosphere. I think Saurabh, you can answer it much more better that are these radio I don't know if these radio waves are absorbed by the atmosphere or not. Saurabh, can you please address this?
Hello.
Yeah,
Yeah.
Saurabh.
Yeah. Can you hear me?
Yeah, yeah.
Yeah. So basically, it's actually related to its frequency, not right? Because the frequency is very low for these radio waves, and they do not have enough energy that they can. Oh no, I think he asked something else.
No, no. The question was, I think, why the long range radio waves are blocked by atmosphere. So I don't
I
think
guess you
that
mean
the
to
radio
say
waves.
it's actually blocked by the ionosphere when we are
Yeah, yeah,
transmitting from surface of the Earth.
yeah.
Yeah,
So,
it's actually not. Yeah, you can answer if you want.
so I was saying that I haven't read about the radio waves being blocked by the atmosphere because they can penetrate, and in fact, we have received the radio waves from the early universe itself. So can you answer that? You are much more into that radio astronomy and all. So I think you can address this question that whether these radio waves are blocked by the atmosphere or not. Saurabh?
Yeah. So basically, these are not sort of blocked, but it's like whenever there is some transmission from Earth towards the space. So these are basically reflected back, and this happens due to the absorption in the particles within the ionosphere, and also at the same time, the particles in the ionosphere itself vibrates at the same frequency. So there is sort of a resonance when they're being interacted with radio waves, which are being transmitted from the Earth, and then it is reflected back. It is due to the energy at those particular low frequencies which these radio waves carry. So that's why. So that's why they do not penetrate much the ionosphere, and hence you might know that when in earlier times when there's BBC telecast from one side of the Earth to another side of the Earth, this is how they basically use for transmission, like with radio waves, like transmitting from reflecting from the ionosphere. Yeah.
Yeah. Okay, thanks a lot, Saurabh. If there are any more questions, you can please ask.
I think there are no more further questions. But if any of you have more questions, they can be forwarded to Rishabh directly on his email, or they can be asked in the comments box after this video has been uploaded to YouTube. So thank you so much, Rishabh, for such an interesting talk. And we'd like to end the series, the exposure series in astrophysics and cosmology by a good response from audience. There were good audience for every talk, a good number of audience who listen to this talk and ask such good questions. If someone asks regarding the certificates, yeah, they'll be emailed you within this particular week. So keep checking your email, and you'll be receiving a certificate on email itself. Yeah. So thank you, Rishabh, and thank you everyone who joined us today and for the whole lecture series. we shall be organizing more events in the future. So don't forget to follow our page on Facebook itself, Stellar Universe One, and also on Instagram. So thank you so much.